Okay, so if we have an adjoint model, we can now take the next step in the derivation, which is to say that when we look at perturbations to the initial condition, they're going to be determined by the Kalman filter. So if we have measurements, that change the state from a background that gave us a control forecast to another one that gives us a perturbed forecast, and all the perturbations are due to the measurements, then that analysis increment is given by the Kalman filter. Right? It's the same equation you've seen over and over again now. All right, so we can now plug that in for the delta x naught. We know how the measurements produce that perturbation to the initial condition. And by the way, I did this sometime between late yesterday afternoon and 3:30 this morning. So the likelihood of a typo on this slide is probably near 100%. But no one's spoken up yet, or they're just being kind. Anyway, maybe it's right. I think it looks pretty good. It's not exotic math. You could probably just eyeball it. So here we are. Now this is where we've arrived. We can find out how that performance metric that we're interested in is going to change based upon the measurements. It involves this adjoint sensitivity gradient and the analysis increment, which comes from the Kalman gain. So now we can look at the sensitivity to the measurements, again taking a d by dy. And again, through the magic of matrix calculus, this is the answer that we get. Here's the y. It's multiplied by these two things. You have to take the transpose, and you get k transpose times the adjoint sensitivity gradient. And we're done. All we need is the adjoint sensitivity gradient, which comes from the adjoint model, and we need the transpose of the data assimilation system. The adjoint of the data assimilation system, right? Somebody did it. Lots of people have done it, actually. So that's it in a nutshell. Okay, so ensemble sensitivity theory, what I will call the key move is this one. If we consider that equation from the last slide that involves changes to our performance measure with the adjoint sensitivity gradient and the perturbation to the initial conditions, if we multiply by delta x naught transpose, we form the prior error covariance matrix at the initial time. All right, and we've got some stuff on the right side. Ooh, I forgot. There's a typo. Right, H transpose. So I'm multiplying by delta x naught transpose H transpose. If you take the expected value, then this is a covariance, and you're left with the sensitivity gradient, which we assume, and as do Langland and Baker, that it's the same as for the control trajectory. And this is BH transpose, right? So there's supposed to be an H transpose here. This is B, right? The left-hand side, if we consider H delta x naught, that's our estimate of the observations, and that's their covariance with the metric. So we have a covariance between what the prior estimate of the measurements is and our performance measure. That's something we can estimate with a sample, which gets rid of the need for the adjoint sensitivity gradient. If we plug in for k, we get here. And now you can see that we have the thing that we're trying to get rid of. dj dx naught b h transpose now gets replaced with a covariance. Right? So I think I've come across this many, many times now. Around the same time we came up with this, folks were coming up with the same idea for replacing the 40 var gradient calculation with a similar sample estimate. That's where n var came from. And I think it's a generic fact that we never want the gradient in a Taylor series. We don't care about the gradient. We care about the change. We care about delta x, delta j, whatever. And that's basically what we're after here. OK, and then we're in the same place. We take the derivative again. And now we have something that we can estimate knowing only the same information we need for data assimilation, which is the map for the measurements, the prior error covariance, the observation error covariance, and this thing that we can calculate, which is essentially the linear regression between the estimated measurements in the ensemble at the initial time and our performance measure. Right? So, yeah, that's all there is to it. Right, so these ideas, this is a picture that just illustrates how these ideas were applied or are still applied in reality. I don't know if they still, are they still doing the winter storms reconnaissance, or is that done?
I think so, but I haven't been following.
For a while there, this was a regular activity over the North Pacific where money was invested, planes were flown to do exactly this. And the idea was as follows. We had some initial time and some forecast time we were interested in, and we would calculate where in a day or so the biggest sources of error would be when we were going to simulate those observations that would affect that forecast that we care about. Right? So we have a lead time to get on the plane and fly somewhere and gather the information. So there is a deployment, and then when we get to the analysis time, we have the measurements from the airplane, we assimilate them, and we hope we have the expected reduction in error in the forecast at the time we care about. This has gotten better over the years, as I said, once they got data assimilation systems that were more in sync with the targets that were predicted. And there's a review paper in the Bulletin of the American Meteorological Society by Sharon Majumdar in 2016, which describes all of this. And I participated in field campaigns with Sharon for tropical cyclones to predict these targets using our ensemble technique. So it's a real thing. Real money was spent on doing this. But I would say that the improvements, even when they were working, were relatively modest. And as I said, they depend on the data assimilation. And in the last 15 years, the problem has shifted from finding the best location to having too many measurements. We have a lot of measurements now, mostly space-based from satellite radiances. So we're getting more into thinking about priority and thinning. And I'm interested in using these tools for the dynamics of the system and something I'll call forecast adjustment, which I'll talk about in a moment. Why does that say theory? Yeah, sorry, that's a stray slide there. Okay, so here's an example from Eugenia's paper. Around the same time, we were coming up with the same thing. And she was showing a comparison, they were showing a comparison between the adjoint method, the ensemble method, very similar to ours, and the actual forecast errors. And you don't have to be able to grok the details, but mainly see that these curves correspond relatively well. That is, they're able to predict with the adjoint and the ensemble method what actually happened in the forecast errors. In this relatively simple model, the Lorenz-Manuel 40 variable model. And then in a more recent paper, I believe this is in 2012, same sort of thing, comparing an updated version of the technique with the adjoint method. It was clear that the adjoint method was noisier than the ensemble method. And I think this was the result you were quoting before, Eugenia. This shows the relative positive impact that the measurements had. You can measure that as a function of lead time from these different methods, and it's roughly about 50 to 60%, even out to a lead time of about 7 days. So it provides you with a reliable, accurate way to measure the impact that your observations have on a future state of the system that you can forecast with the model that you have. The next thing I'd like to show is how to apply this to system dynamics. And here I'll talk about weather now, the extratropical transition of tropical cyclones. I'm sure around here you're very familiar with these things. Tropical cyclones form over the subtropics and the central and western Pacific. They wander to the west, recurve, and then they affect Southeast Asia quite frequently during the warm season. And we're trying to understand sources of forecast error and also to find the most important measurements. Those are kind of the three goals. And what we're looking at here is for a tropical cyclone that occurred 2005-ish or so. We're looking at the mean sea level pressure on the left 0, 24 hours, 48 hours. The contours show you the pressure. So low pressure is the tropical cyclone moving northward with time. The colors show you the uncertainty, which is assumed to be proportional to the anticipated error. So the error grows very rapidly in this 48-hour forecast. So that's a bad thing. We don't want to have large errors in our forecast of tropical cyclone affecting the populated areas here. At 500 hectopascals, similar growth and error. So it's a very uncertain situation for a high-impact weather event. And when we look at conventional observations in the 24-hour forecast on the left, 48-hour forecast on the right, again, 500 hectopascals. It's kind of a measure of the jet stream level. Here we're looking at the mean sea level pressure field on the left. You can see that there is a sensitivity in a 24-hour forecast. It's relatively close to the tropical cyclone. Little shifts in the position are what are contributing to the error there. In the 48-hour forecast, it's highlighting interactions with this feature in the jet stream. So this feature right here is called a trough. And the dipole and the colors there are showing that the relative position of that trough in the west-east direction corresponds with the anticipated error in the intensity of the tropical cyclone. And this is known from the physics of extratropical transition, that how the tropical cyclone interacts with disturbances in the westerly jet stream strongly controls their intensity and their motion. So we have a way of objectively identifying that, and we could do it for the forecast errors as well. The forecast errors are basically showing the similar thing. We can only compute that after the fact. The other one we compute before the fact. And then I think this is probably the most interesting part of this, is that we can do hypothesis testing. And this is where, in my lab, we've done this repeatedly. We extract the sensitive signals, and then we use those as hypothesis tests to perturb the model. And if we perturb the model with these fields, we can then look in the fully nonlinear model what the response is. So what we're trying to do here for two different tropical cyclones is predict the change that a change to the initial condition will have in the forecast. Okay, so for a 48-hour forecast with our ensemble sensitivity analysis, we can predict, we can control the intensity of the tropical cyclone. Right? In the forecast, using this theory, we can raise the central pressure or we can lower it by perturbing that initial state. And then on the ordinate is the actual result from running the fully nonlinear model, from the WRF model for those of you that know weather forecasting. And then essentially if we were to fall on the diagonal, our linear predictions would be validated. And you can see for small amplitude perturbations, it does work really well. These are error bars since we did this many, many times. But then it sort of rolls off in both directions. So this is nonlinearity saturating the forecast. But you can still see these are big changes. 15 hectopascals is not a small change in the intensity of a storm, nor is negative 15 hectopascals. For this other storm, Nabi, we see similar responses and a bit of an asymmetry for making the storms more intense or making them weaker. So we can then go and say, what is it about these perturbations to the initial condition that is responsible for the change in the intensity of the cyclone? So it's a way of using these tools to understand the dynamics of tropical cyclones and their interaction with other features in the flow. Again, I know if you work in some other field, this is all kind of gibberish to you. The take-home message is you can use tools of data assimilation to understand the physics of your system that you may not have known about before. And this is for changing the forecast error. Can we reduce the error in the forecast? And for both of these storms, the answer is yes, up to a point. And then we can't reduce the error any further. we probably could, and as a matter of fact, I think the student who did this relinearized here, and we can push this curve a little bit further toward the negative direction.